set up. So we are almost done with the semester. We've got today, then Tuesday for new. That's pretty much all the time we'll spend on new stuff, today and Tuesday. Then following these last two classes will be largely review. We'll have our last quiz that last Tuesday after Thanksgiving. We got to check out a lab on Wednesday, and we'll go through some more review things. So the final, if you saw the schedule, all the Chemistry 121 classes take the final all together at the same time. It is on the Thursday of exam week, Thursday afternoon. So that would be, what's the date on that? Let me see. So that's the 12th, December 12th is the final exam. It will not be in here, it will be in larger lecture halls. We'll let you know exactly which rooms they'll be in when we get closer. It'll be at 3:30 in the afternoon, so make sure that you have that Thursday afternoon available. It should not interfere with any other exams or any other exams on campus scheduled at that time. So you should not have a conflict there. If you do, for some reason, have something else going on campus, then let me know as soon as you can so we can figure something out between either us or whatever that class that is. The exam is a little bit different format from the what we've done so far. It's a national standardized exam given by the American Chemical Society. It is entirely multiple choice. I don't know the exact number, but I believe it's about 65 or 70 questions, and you've got about 2 hours to do it in. So it's a little bit faster paced. There's no open free response. You'll be in this environment of a big lecture hall with a bunch of people, kind of like a standardized testing environment. You'll be filling in the sheets and all that kind of stuff. You can't. A couple of things that are different about it, because it's a national standardized exam, you can't have any personal items with you while you take the exam. So all of your anything you bring in, like a bag or a coat or that kind of stuff, all needs to be kept at the front of the room, including your phone, wallet, all that. And what else is special about it? And you can't leave until the exam is done. So make sure you go to the bathroom or something beforehand, because if you leave the room, you have to turn your exam in, and then that's the end of it. So that exam is scaled based on the national statistics. So your raw score is not the same as your calculated score. To study for that exam, the reason we use that exam is because it is a good measure of what you have mastered through the whole semester. So studying for the exam isn't really different from what you've done so far. Certainly look at all your previous exams, especially the multiple choice sections. And if you want additional materials, the American Chemical Society does sell some study materials that you can order. Let me see if I can find that for you. Yeah, if you just look up ACS Study Guide. There are a couple things that you can get, but I want to just caution you against some of it a little bit. Okay. So we are general chemistry. There is a study guide book that you can buy. It covers the entire semester of general chemistry. So it might be useful if you plan on taking the second semester, because then you'll have that for both of them. But for just this semester, you'll only be using about half of it. There is also an online practice exam, but again, this is for the full year exam. So if you want to try it, you can try it, but about half the questions will be stuff that you haven't learned yet. So that's up to you. We'll go through some practice stuff the last week of class also. Any questions about any of that stuff, the final? If you do want to order the study guide, I don't know if you can get it from Amazon or places like that, but if you want to buy it from them, certainly get it ordered as soon as possible, so there's plenty of time for it to ship. I think it comes from Wisconsin. I think the exam institute is in Wisconsin. At least it used to be. So it usually comes fairly quickly, but we want to give it a little time. All right. So you're good with that? Make sure you have that Thursday afternoon available for the final. Okay. The stuff we're going to be talking about now, we're actually going to go back to Chapter 6. So we skipped over Chapter 6, which was Thermochemistry, earlier in the semester. And we're not going to do the whole chapter. We're just going to kind of pick pieces here and there. And then we're going to do the same thing with Chapter 13. And that's all the new information that we're going to have this semester. All right, Chapter 6 is all about thermochemistry. And the reason we don't do the whole thing here is because thermodynamics in general is a big part of the second semester course. So if you go on and take Chem 122, you'll do way more with thermodynamics than this. But if you're going on to other classes or just other non-chemistry things, some of the basic ideas of thermodynamics in Chapter 6 are worthwhile. So we're going to look at some of those. All right, the chapter starts with an allusion to hand warmers. Has anybody ever used those like little package hand warmer things? You like open them up, kind of go like that. They're like a little bag of stuff, and they get really hot. You can put them in your hand, in your gloves. You can put them in your boots in the winter, and they keep your hands warm. How do you think that works? What? Chemicals, yes. Any ideas? What's going on in there? You actually don't have to rub it. You just have to open the package. So what does that tell you? Yeah, it reacts with air. What part of air would you guess it's probably reacting with? Oxygen. Yeah, that's exactly right. So it's an oxidation reaction, or an oxidation reduction reaction, where iron metal reacts with oxygen gas to produce iron 3 oxide. So the stuff, all that's in those hand warmers is very finely shaved iron, and then it's packaged in an oxygen-free environment, so that it stays iron metal. And then once it gets exposed to oxygen, the iron oxidizes, the oxygen gets reduced, and you make iron oxide, which is rust. And that reaction gives off heat. So another way we could write this is we could actually put that right in the equation and say that heat is produced in this process. So what do we mean by heat is produced? Because there's a law of conservation of energy, which we've mentioned a little bit, that says that energy can't be created or destroyed. You can't make new energy that doesn't already exist. You can't destroy energy that is already existing. So what's happening with those iron shavings when they oxidize? We say that it's getting hot. We say that heat is being produced. But based on conservation of energy, you can't just create heat out of nothing. So what's really happening there? How can we explain that? Is this violating the law of conservation of energy? Do you think that this reaction violates that law? Probably not, right? So what's happening? way that we can think about this, and the way that we will think about reactions in this chapter is converting energy from one form to another, or transferring energy from one place to another. In this case, there is chemical potential energy inside those species, inside those elements, and it's being converted to heat energy. It's being released and pushed out to the surroundings. So we're not creating new energy. This energy was already inside those atoms and molecules. It was simply released and transferred out. So that's what we're going to be talking about a lot in this chapter, is this idea of transferring energy. Where does energy come from, and where does it go to? All right. So let's make some definitions here. We know the law of conservation of energy. So we're going to always be talking about transfer of energy. And to do that, we need to think about two domains. We're going to talk about the system, and we're going to talk about the surroundings. The system is whatever we're investigating, and it's arbitrary. We're choosing what to focus on in the system. So we choose something to focus on, and then the surroundings is everything else. Again, arbitrarily chosen, but chosen in a way that makes sense for whatever we're trying to do. So in that previous reaction, our system is the chemicals, the atoms and molecules in the hand warmer. The surroundings are everything else. So we can say that in that example, energy flowed from the system out to the surroundings. But we could have, chosen something else there too. We could have said that the bag that the hand warmer is contained in is the surroundings, is the system, and everything else is the surroundings. In that case, energy is flowing from the surroundings to the system, because the energy is coming from something else, from outside and going into the bag. The actual bag part of the bag. So how we choose that just depends on what makes sense for the particular question we're trying to answer. But those are the words that we're going to use for that. So let's look at a couple different ways of transferring energy, a couple different kinds of energy. So first, do you know the difference between potential energy and kinetic energy? Anybody throw out a definition there? Yeah, so kinetic energy is energy of motion, so something in motion. Potential energy is energy that is kind of stored in some way, right, that hasn't been released. There's not a third type of energy, but there's a third way that we often describe energy, which is thermal energy, so the energy of something being at a given temperature. Thermal energy is actually a type of kinetic energy, because we know from other stuff we've done this semester that the Kelvin temperature is proportional to the speed of the atoms moving. So molecular motion gives rise to thermal energy. So we've got kinetic energy and potential energy. And then we've got the internal energy. So the internal energy of a system, which we will give the letter capital E, is all the kinetic energy in that system plus all the potential energy in that system. And internal energy is a state function. A state function is a quantity that only depends on its starting and ending value, and not how you get from the starting to the ending value. A state function depends only on the current state of the system, and not the mechanism by which you get to or from that. Okay, so for an example not related specifically to this, but helpful nonetheless, I think. Take a look at this picture. Oh, there it is. Ah. Sorry, keep going too far. Okay, it's this one, this hill. So imagine you're climbing a hill. There are various quantities at work here. The altitude is a state function. So the altitude only depends on your current height relative to sea level. It does not depend on what path you took to get to that height. Your change in altitude, so like you climb the mountain, your change in altitude only depends on where you started and where you ended. There are lots of other quantities here that depend on the how you got there, like distance traveled. So if you took path A, you would travel 12 miles. If you took path B, you would travel 5 miles. So you have a totally different distance traveled based on which path you take, but the overall change in altitude is going to be the same. That makes sense, right? So we'd say altitude is a state function because it only depends on the final and initial values. Energy is the same way. When we talk about the total energy of a system, we only care about what energy did we start at and what energy did we end at. And there's lots of different ways we can get from one energy value to the other. So things like heat, different ways of transferring energy, those are not state functions because we can take different paths to get there, but the overall energy is a state function. So anything that's a state function in thermodynamics is generally given with a capital letter, and things that are not state functions are usually given as a lowercase letter. So internal energy is E, which is the total kinetic and potential energy. And so we often talk about the change in energy, or delta E, and that's how we can describe certain types of reactions. So let's take a look at a reaction, a different reaction here. Let's take a look at making carbon dioxide from the constituent elements. So we take carbon and oxygen, and we make carbon dioxide. All right. So we can portray the change in energy here in a few different ways. So let's first do like a graph. So let's plot the internal energy, E, and we'll have our reactants and our products. So our reactants are here, carbon and oxygen. Our products are here, CO2. Our products are lower in potential or in total internal energy than our reactants. So that means that overall, the delta E of the system, of whatever you're doing your reaction in, is going to be less than 0. It's going to be negative because we're losing that energy. We're transferring it out to the surroundings. So in this example, the change of energy for the system is less than 0, and the change of energy for the surroundings is greater than 0. So the energy is flowing from the system, from these chemicals, out to the surroundings. And what do you think would happen if, yeah?
How do we know carbon and dioxide are, like how do we know they're higher in energy?
We don't. I mean, I just told you. But like, no, that's next. We're gonna see how we can actually look up to figure that out. Yeah. Yeah, we don't know that yet. Just from looking at the things. So what do you think would happen if we did the backwards reaction? How would the energy values change? If we took carbon dioxide and broke it up into both elements, carbon and oxygen, what would the energy values look like? What would the delta E for the system be? Right, exactly. The signs would just switch. So so it's a state function, right? We have the same molecules. So we would expect that if we do the opposite reaction, that we get the opposite signs for the energy. Okay. All right, so there are two ways that a system can exchange energy with its surroundings. There is heat, which is generally given the symbol lowercase q, and there is work, lowercase w. Heat, we've been talking about heat. We haven't really talked about work yet. Work is a force applied over a distance. Right? So you push something, you're doing work on that. And in general, some sign conventions. I will copy this from the book here so you can see it. Because again, these are arbitrary designations. You can decide, or we could decide how we want to do this as long as everything stays consistent. But in order to keep everything consistent, there are some conventions that we follow in general. So for heat, if a system gains thermal energy, so that means the energy is flowing into the system, we give heat a positive sign. And if it loses that thermal energy, it's negative. So the examples we've seen so far, in both cases, we're losing thermal energy. For work, if the work is done on the system, the sign is positive. So if I am pushing this ruler, I'm doing work on the ruler. If the ruler is our system, then the work change for that ruler is positive, or the work for that ruler is positive. And then the total internal energy, which is the heat and the work, the change in internal energy is going to depend on the heat and the work together. We talked about that. Energy flows into the system is positive, flowing out of the system is negative. So let's look again, like we did with the hill, at a non-chemical example first. And then we will look at how we apply that to molecules. All right. So let's take a look at some balls on a smooth pool table. We're going to take our ball on the left. We're going to shoot it at the purple ball on the right. It's going to hit the ball and transfer its energy to that ball. So let's look at the different types of energy that are transferred there. There's friction with the surface of the table. So the first change in energy is the heat that is lost by that ball. So the ball is our system, and the ball is transferring thermal energy to the table via friction, and we're saying it's about 0.5 joules of energy. Okay. So then once it gets to that ball, it now has 4.5 joules of energy left, like the kinetic energy that it starts with as it goes. Okay. Once it hits the ball, it transfers the rest of those 4.5 joules of energy to the ball via work, because it's now pushing that ball. So the overall change in energy is negative 5 joules, because that white ball has lost 5 joules of energy. it's done minus 0.5 joules of heat, transferred 0.5 joules of heat, and it's done, it's lost 4.5 joules of work, so it's transferred 4.5 joules of work away from the system, because the system is doing work on the other ball in the surroundings in this case. All right. So if we change that, they're saying this is a relatively smooth table. What do you think happens if we now look at a rough table, a table that's, you know, old and has a bunch of junk on it? But how? So which? Yeah, we're going to lose, right. So you're right. We're going to lose energy faster, and we're going to lose it as heat. So that first loss of heat, losing the energy from the ball to the table, is going to be greater in magnitude, and that means there's less energy to transfer via work to the purple ball. So let's see if that's right. Yes, so we'll say on a rough table, we're going to lose 3 joules of heat to the table, so minus 3 joules of heat. And then our kinetic energy is less once we get to the purple ball, so there's less energy to transfer to the purple ball. All right, so that's heat and work. So the total energy is going to be the sum of the heat and the work. Okay, so now let's transfer that to some chemical systems, because that's really what we care about. I mean, this is fine too. We can care about this too. How do work and heat manifest themselves in a chemical reaction? We already talked about heat. You know, that we can, like in those previous examples, that we can lose heat. What happens with work? Yeah. Okay, so particle size is going to have something to do with how these things are transferred. Yeah, that's going to get a little bit into a little too much detail for what we need right now. So you know, if you go into like take chemical engineering, thermodynamics classes and things, they definitely talk about all that. If you imagine doing things at really large scale, chemical reactions, you have to really be careful about how the heat is being transferred in and out. You can have big problems. Yeah, so that's all part of the issue. The type of, so let's go back to this idea of work. The type of work that we do in chemical reactions is called pressure volume work generally. Because if you imagine, you know, something reacting in some sort of a vessel, the way that system is doing work is by kind of pushing up against something. So the classic example is in a piston, like in a car engine. Where's a picture of that? All right. Well, we don't have exactly the same picture that we've got in our book, but there's our car engine. Right, so you have some fuel and some air injected into a piston that then combusts, and then that is doing work on the piston by pushing it away, and that's how your car goes, because you're having this chemical energy turned into work energy. Of course, it also gets hot, so there's also heat being released as well. One of the reasons that combustion engines are not as efficient as they could be is because they're losing a lot of that energy as heat. But that's basically how chemicals can do work, is by expanding against something like that. So that's in a closed system like a piston. What if we're just doing a reaction out here? We do some chemical reaction. Is that reaction doing work? What? Kind of? Maybe? Is it pushing against anything? The air. That's a thing, right? Remember chapter 5? What is all the air doing right now to us? Yeah, it's pushing on us, right? There is a pressure. being exerted on us by the atmosphere. There is atmospheric pressure. We often ignore atmospheric pressure because it's just everywhere, but it's there, and it has huge effects on all kinds of things. So, so when something is just reacting, it is actually pushing up against that atmosphere, but because the atmosphere is sort of everywhere, we often consider that to be constant pressure. So we're not changing anything when a reaction pushes against the atmosphere so much. And so there's a derivation in the book on page 267 about why we can kind of not worry so much about that. So this symbol that we've seen and that we've dealt with, H, is called the enthalpy. And we've sort of used this interchangeably with energy, E. But it's not quite the same. The enthalpy is the sum of the energy and the product of the pressure and the volume. So basically correcting for this pressure volume work that's being done. So the internal energy plus the product of pressure and volume. Now the actual state of the system, the enthalpy H, is often not what we care about so much, but rather the change as a result of a particular process. So we often talk about the change in enthalpy as delta E plus P delta V, not W. Now, energy is the product of the heat and the work, or the change in energy is the product of the heat and the work. This P delta V term, the pressure against the volume, is the work being done by the system. So that's the negative work. So you end up with a positive work, negative work, and they cancel. So ultimately, the change in enthalpy is the heat at constant pressure. So we often use a little bit of a P there. So it's a subtle difference between delta H and delta E. They're both measures, they're both state functions or measures of the internal energy of a system. But the E is the measure of the kinetic and the potential energy, all the energy exchanged with the surroundings. And the delta H is only the energy exchanged under conditions of constant pressure, which is like open kind of atmospheric condition. So that's why delta H is often so useful for chemical reactions, because we're usually in a constant pressure situation. We're not usually doing a chemical reaction in an engine or something where we're pushing on a piston. So it's sort of a way of not worrying about the work too much. All right. So this way, we can more carefully and specifically use these terms endothermic and exothermic. We've kind of thrown those around before, but now we can say that in general, a chemical reaction with a positive delta H endothermic and one with a negative delta H is exothermic. In the next semester, if you want to take this, then you'll really carefully separate these terms. When we say endothermic or exothermic, when we use that term therm, we're specifically talking about the enthalpy, only the heat. There are other terms, endergonic or exergonic, which are talking about the energy flowing in or out of the system. The total energy, not just the heat. All right. So one thing we can do with this then is we can figure out energies of chemical reactions from looking up what we call standard enthalpies, standard states and standard enthalpy changes. So you can look up tables like in the book. There's one in the back here. Somewhere. Here. And if you want even more things, you can look it up in like a handbook, like the Handbook of Chemistry and Physics. You can look up these compounds and find the enthalpies, the standard enthalpies of formation for these various different species. All right, so let's look at how we can use those. So the term for or the way that we see a standard enthalpy is a little degree sign like that. This tells us that it is a standard enthalpy change, which means it basically follows some rules. So like for a gas at a pressure of exactly 1 atmosphere, for a substance in solution, it's a concentration of exactly 1 molar. And so for a compound, the change in enthalpy when 1 mole of the compound forms from its constituent elements is called the standard enthalpy of formation. The standard enthalpy of formation for any element in its standard state is 0. So we can look at a reaction like this. And there are some different forms of carbon, so we're going to specify that this is graphite. Carbon reacting with hydrogen gas makes methane. So we would say that the standard enthalpy of formation for carbon by itself is 0. The standard enthalpy of formation for hydrogen by itself is 0. And so if we measure the enthalpy change in this reaction experimentally, then we find that the enthalpy change for this reaction is minus 74.6 kilojoules per mole. Okay? Which means that the standard enthalpy of formation for methane, CH4, is minus 74.6 kilojoules per mole. That's just like a value that we can look up on a table. We can look up methane and find that. So there's a bunch of different enthalpies of formation. They're also sometimes called heats of formation. So if you don't like the H standing for enthalpy, you can think of it as heat, although we know heat is actually Q, but it's heat-like. So knowing this, we can look at a reaction, and we can calculate this overall energy change, so whether it's exothermic or endothermic, based on the standard enthalpies of formation. We did this a little bit in Chapter 9 using the bond energies. But this method is a little bit more powerful and more broadly applicable. So let's try it. Let's look at the combustion of methane. So here's another reaction. Methane plus oxygen gives CO2 plus 2H2O.
And we want to know, not the formation, what is the standard enthalpy of this reaction? So we think about it kind of this way. We're going to take the, kind of like what we did in Chapter 9 with the bond energies. We're going to take the reactants and decompose them into their constituent elements, and then put them back together as the products. And just for kind of a visual look at this, pull this picture from the oh no, I think this book doesn't have the same pictures as mine. Okay, well we'll just do it. Let's make our scale for enthalpy. So first we need to look up some standard enthalpies. Just move that out of the way. Okay, can't move that out of the way. So we're going to look up our standard enthalpies for our different species in this product, and this is, you just look up on a table. So our table is page 276 in the book. So I'm going to look up methane, which is minus 74.6. Oxygen, O2 gas. Oh yeah, that's 0 because it's in its elemental state, right? It's an element. Then we've got carbon dioxide, minus 393.5. And water, minus 241.8. All right, so we're going to think of the overall energy of the process as the reactants, methane and oxygen, breaking down into carbon, hydrogen, and oxygen, and then reacting into carbon dioxide and water. So here's our reactants, CH4 and 2O2. We'll start with them like right here. So do we go up in energy or down in energy to decompose these into their constituent elements? And by how much? Remember that the heats of formation are just that, heats of formation. So if we're breaking something down, then we're going to flip the sign on the standard heat of formation. So in this case, our standard heat of formation for methane is minus 74.6 kilojoules per mole. Are we forming methane or are we breaking it down? First. Breaking it down, because it's a reactant. Reactants get broken down, products get formed. So we're going to break down the methane, which means that we have to go up in energy by 74.6 kilojoules per mole, positive. Does everybody see why we did that? We're thinking about this reaction as the reactants breaking apart and then the products forming. So the reactants are going to have the opposite sign for the heat of formation, from their heat of formations. And then the products are going to have the regular sign of the heat of formation. We ignore oxygen in this case because all elements have 0 heats of formation in their standard states. Okay, so now we're up here. Switch colors here. And up here is the constituent elements. We have solid carbon. We have hydrogen. And we have 2 oxygen. Everything stays balanced, right? So these are the constituent elemental forms. And now we're going to form the products. We're going to form CO2 from the carbon and one of the O2s. And then we're going to form H2O from two of the hydrogens and the remaining oxygen. So let's draw that. We're not exactly in scale here. Well, here, let's just make it bigger so it looks more realistic.